Today we're fortunate to have Hyungwon Chung from OpenAI. He's a research scientist. Interestingly, he actually did his PhD here at MIT, but it wasn't on machine learning, right? I think it was on renewable energy and energy systems. And since then, he's gone to Google Brain and then moved over to OpenAI. Hyungwon's well known for his work on large language models. So some of his works include scaling Flan T5, Flan PAM, and T5X, which was the training framework used to train the POM model. So I'm very excited to hear him hear from him, the advances in LLMs, and let's welcome him back with a round of applause.
Thank you. It's really good to be back. And today the title of my talk is Don't Teach, Incentivize. My research is on developing general intelligence and as opposed to a specialized intelligence. And when doing that, it's just impossible to enumerate everything that we want to teach the model. And just there's so many skills we want from them, and we don't even know all of them. So I think the only feasible way to get to general intelligence, in my view, is to weakly incentivize the model so that the models themselves figure out themselves. So before we get to the details of the talk, let me share the goal of today's talk, which is somewhat different from most of the technical talks in that I'm not going to share specific technical latest paper of mine or experimental results. Instead, I want to share how I think with AI being a running example. And you might wonder why. In my view, we, the technical people, focus too much on solving problem itself. In my view, we should put more attention to finding great problems to solve. And the best researchers I've seen in my career are not necessarily the strongest technical people. They certainly are, but that's not the defining feature for them. Instead, they know how to find the most impactful problem to solve. And I think that comes from having a great perspective. And I think having this importance of having good perspective is undervalued, and I want to use this chance to share mine. And by no means I'm saying I have a great perspective. My hope is that by sharing mine, it sparks interest in this kind of conversation among some of you. And we as a community will discuss more of this and hence become better at finding better problems to solve. So let's get started. Brief outline of this talk is first share my perspective, and everything I say will be pretty much on scaling. And I'll define what my version of the scaling is later. But we'll develop that perspective with very general AI research. And with that, we're going to specialize into this language models that I'm working on. So that's overall view. Let's start with the most important data points I know in the entire AI. So this is from Rich Sutton's keynote speech last year. And on the x-axis, we have a time from about 1900 to 2020. And then on the y-axis, we have compute power the calculations per second you get if you pay $1,000. And this is in log scale. So what we're seeing is that compute power for a given amount of dollar increases exponentially over like 100 years. In other words, compute cost is going down exponentially. And I don't know any other trend that is as strong and as long-lasting as this one. And whenever I see such an incredible trend that is way beyond my intuition, I think about two things. First, I should not compete with this. Second, I want to leverage this as much as possible in every aspect of my career and life. So we're seeing this hardware exploding exponentially. So we as a people, some of us developing softwares and algorithms should catch up on that. And in particular, we need more scalable methods that can better leverage ever-increasing abundance of compute. So more generally, what is the job of the AI researcher? It's to teach machines how to think. And one very common, unfortunately, approach is that we teach the machines how we think. But do we know how we think at the very low level? We don't. So what we're doing in this kind of approach is that we're teaching what we don't fully understand and in a limited language of mathematics. And this approach typically poses a structure to the problem which can become, or typically becomes a bottleneck when we further scale up. And bitter lesson again from Rich Sutton is summarizes phenomena, saying progress in AI over the past 70 years essentially boils down to developing progressively more general method with less structure and add more data and compute, in other words, scale up. That's a very strong statement since we have seen many, many different types of progress, but all of them just summarize into this very strong statement. And I totally agree with this. And in fact, I think this is the single most important writing in AI. And I go back to this essay many, many times. So I'd strongly recommend it if you haven't checked it out. So this is my graphical version, illustration of the same idea. On the x-axis, we have a compute. And you can think of it as just compute or data, and or data. Y-axis, we have a performance. You can think of it as some kind of an intelligence metric, very much of a cartoon. So two methods we can think of, one with the more structure, one with less structure. And what we see over and over is that the method with the more structure typically starts off quickly because the structure itself serves as a shortcut. And that serves well until it doesn't, and it doesn't really scale up. In contrast, the one with the less structure typically starts off as doesn't work because we give too much freedom to the model and it doesn't know how to utilize it until we give enough data and compute and good algorithms to leverage that. And at some point, it just gets better and better. And we call this more scalable solution. So one maybe concrete example is when we have this like classical machine learning algorithms like SVM that could be compared to deep learning, it'll be more like a more structured version. In particular, the kernel methods, things like that, are structures supposed to learn what kind of representation we should put into the data, whereas deep learning, we give, okay, model should learn the representation given this problem. So that didn't work, but it eventually won because of this more scalable nature. And within this deep learning, we see a lot of this hierarchical. One is more scalable deep learning approaches, and one is not. So let's make some sobering observations. Clever structures posed by human researchers typically become the bottleneck when scaled up. What is good in the long run almost necessarily looks bad in the short term, because we're doing learning-based method, and we're trying to give machines as much as freedom as possible. And so what's going to win in the long term will look bad in the short term. So that's kind of a very different dynamic from other scientific fields. And compute is getting cheaper faster than we're becoming better researchers. And so we should not compete with that. Instead, give machines more degrees of freedom and let them choose how they learn. It can be different from what humans think of as a human intelligence, but I don't think human intelligence is any form of upper bound, and we care at the end about the intelligence and the value it creates. So we should not dictate how that looks like. And maybe if this observation might be obvious to you, but at least many people find it not obvious, and there are many reasons. I want to talk about one reason that is less talked about, which is that researchers want to add modeling ideas because that's academically more satisfying. And some people think just scaling up is not scientific or even interesting. And I often hear this phrase, that's just boring engineering. And I would like to ask this question to such people: why are we doing AI? Why are we developing any technology for that matter? And I think the ultimate goal is to create value that benefits humanity. And that is more important than anything, any ego of the scientist. And so really, we should be focusing on maximizing the value generated by AI while minimizing the downside, regardless of which academic discipline achieves the goal. And it doesn't matter whether the thing I studied for 10 years is not the most scalable now. I have to be really intellectually honest about what I'm really after, which is to create value. And if it's not the most scalable method that leverages the compute the best possible way, I should rethink and learn. And I think this is kind of the approach that I've been taking, including, so my topic has been changing, but in the theme of better leveraging the compute, it hasn't changed. So I've been talking about scaling in a kind of a loose way. I want to define a little bit more precisely what I mean by that, because it's a little bit different from the common definition that is used often, which is that doing the same things, we're more machines. I think this is true, but not that interesting. My version is that it involved first, identifying the modeling assumption or inductive biases that bottlenecks further scaling, and second, replacing it with a more scalable one. And if we think about this previous example of SVM versus deep learning, I think of that as a scaling because we want to put in more compute, and SVM was just bottlenecking there. And we identified that this data representation was the bottleneck and replace it with the learned representation. And that, I think, is scaling, in my view. And I think a more interesting type of it. And many instances of this. And in my personal viewpoint, what OpenAI is really doing well relative to other places is that researchers there really abide to this kind of idea, whether consciously or not. This is really what we're doing. We have this so much compute that's available or going to be available soon. And the question is, how do I put in? It's actually quite difficult if you think about, if I give you like $100 billion of compute, can you use it in the right way now? And I don't think anyone knows really well how to do it. So we are really finding a way to put ever-increasing compute. And that's the researcher's job. So that's my perspective. Everything I'm going to talk about from now on will be based on this scaling and bitter lesson. And so let's talk about this language models. I put it like large language models, LLMs, because it's just a common acronym. But I kind of think that both L's here don't really mean much. Large is a very subjective term. Large models of today will be small models in a few years or even next year. And the other L, language, we'll talk about why I don't think it's a good term. So all the LLMs so far use transform architectures, and we don't have to look into the details. We're going to take a very functional viewpoint and think about this transformer as a sequence-to-sequence mapping with just a bunch of map models. Input is a sequence of vectors, each of size d, and vectors. Output is the same thing. At least during training, that's what happens. And the interaction is done by a bunch of map models. So just because we have probably a diverse audience, I just wanted to bring everyone in the same page and just have a crash course in what the next token prediction process is doing and go into some of the implications of that process. So we start with the sequence model, and one particular sequence we can think of is a sentence, which is a sequence of words. And the first step is to tokenize it. And why? Because we need to represent the words in a computer, and which requires some kind of an encoding mechanism. And here we usually use this mapping of the integers. So we define a finite set of integers, say like in this particular case, 30,000, I think. And each word or token gets mapped to an integer that's going to get changed during training. So now we have a sequence of integers instead of the string, and we can now do an embedding. This is not necessary by any means, but this is more common ways of doing it. Now, each integer representation of the sequence element, in this case a token, is represented in the vector of size d. And now let's think about what we want from a sequence model from first principles. The sequence model is a model that just models the interaction between the elements in the sequence. And so the transformer is a particular way of doing sequence modeling where that interaction is modeled as a bunch of dot product. So we take the two vector representation of the elements, take the dot product. If it's high, then we think this is semantically related, then the two pair. The other pair that has a low dot product. And we don't really dictate what that means semantically. We can try to understand it, but I think it's not really the easy or maybe meaningful. And so after a bunch of dot product, we get a representation of same size vector, but now each vector knows about the presence of the other ones and hopefully somehow measures some relevance between them and have a rich, deep understanding of what's going on. And so the final process of this, take the loss function. We need a scalar just because we want to use a gradient-based optimization method. And so that we get the scalar. Now take the gradient of this scalar with respect to all the parameters in the model and then update using some kind of gradient method. That's one step. Repeat as many times as possible. And that's the training process. So next, let's talk about this taking from this vector representation into a single scalar, which is the optimization objective function. And in this particular case, most large-scale training nowadays use some form of next token prediction. So I think it's worth looking into it more in more detail. So I put this original sentence back in this slide. So what we're doing is essentially given many, the first token, try to predict the next one. As I mentioned, this encoding mechanism we start with the finite vocabulary, which is, say, like 100K items. And the model outputs the probability distribution over them. So the numbers here should add up to 1. And our hope is that the model learns about the structure such that the next token, words, gets higher probability than something like intelligence. Many intelligence doesn't make sense. And after that, we do, again, given many words, try to predict the next token, which is don't, and so on. So that's the process. You do everything until the end. So this is thinking about conditional probability. We get given all the previous tokens, try to predict the next one. An equivalent, maybe more, just natural to statistics background people, is that this conditional probabilities, when multiplied together, becomes the probability of the entire sequence. And that's what we're maximizing. And this is the maximum likelihood framework. But I think it's more kind of intuitive to think about multitask learning, each predicting the next token given everything before. And crucially, each prediction gets the same weight. We don't really distinguish which token is what. And in industry scale, we just do it in the web scale text data, feed that into the transformer. That's where magic happens. So what kind of magic do we expect? This is a paper from Palm paper when we worked at Google. The reason I picked this is because nowadays people don't really report in the pre-training only. So if we want to understand the next token predictions task performance by itself, we kind of have to go back to the old paper. Here, the details don't matter, some bunch of big bench tasks. And what we're showing is that just by predicting the next token is actually getting better than many human average performance. And I don't know, but to me, this just doing next token prediction and getting better at so many different things is just magic. I still find it very surprising, and I think we should not take it for granted. So let's make some observations about this next token prediction. We don't directly teach any of these like linguistic concepts, like the next token is a verb, next token is whatever. We don't do any of that. But somehow, just by predicting next tokens, the languages just come emerge, and that I think is almost like a byproduct of doing such tests. Languages are learned, and I would go even further to say the best way to teach language is not to teach language, and because we don't want to put any structure in the machines learning about the language. And so that's a very interesting byproduct. And that's why I don't think language model, the L here, is a kind of a misnomer, because we're not teaching any language. Language model is about learning some word knowledge, and language is one representation of that. And so the other interesting thing is that the model can do some reasoning, math and coding and all these things, even though we don't do any specific teaching of that. So I think all the researchers I know have essentially some version of the hypothesis as to why this thing works so well. And I don't think there's any consensus in why this thing is so good. And I do have my own version, which has helped me quite a bit in thinking about my research projects. So I want to share this. So my version is that it's a massive implicit multitask learning, implicit in the sense that we don't directly specify what are the multitasks that we're asking the model to do. They're just imposed by the diverse corpus that we're using. And so actually, let's think about this. I think now take it for granted the language models are doing good job, but it's probably useful to think about the suffering the model goes through and during training. So let me try to illustrate what is it like to do the prediction of the next token. And here I'm going to show a sentence, and the underlined one is kind of what I'm trying to predict. And in doing so, let's do with the least effort possible. Try to do it with any shortcut as possible. And so if I want to predict this, the terrible movie was really, and then try to predict boring, I can probably take the shortcut and say, okay, terrible is a negative thing, so it's going to be something negative, and then it's movie. So maybe I can use that pattern matching to get the word boring. Now I give you one more sentence. After the earning call, the share price of Google went up by 5% from 1,000, ending in 1050. Here, because I want to do lowest possible effort, I think about, can I recycle the skill that I learned from the first example to do this? And it's not, because it's irrelevant. I have to learn some kind of a new skill, which is math. Third example, it's a completely different language now. So I cannot recycle this because I need to learn new language. So the third skill I learned. Fourth, the first law of thermodynamics, which is my favorite topic. used to be, is often called conservation of energy. Now, in order to predict this, we need to know we cannot recycle anything above, have to learn a new skill, which is scientific knowledge, and so on and so forth. When we do it at the web scale, we're talking about billions or maybe even trillions of sentences, and that because each sentence contains multiple next token on the order of maybe thousands, we are talking about trillions of task types that can be framed like this. And if you're trying to solve this, and at some point just intractable, even for large models, this doesn't seem like a tractable thing to do. And I think if we really want to do it with the lowest possible effort, maybe it's more amenable to think about, okay, what are the general skills that I can learn and apply to as many task types as possible? That probably is an easier path now if we burden the model enough with trillions of task types. And I think that's my really hand-wavy way of thinking about multitask learning hypothesis. Beyond some scale, it's easier to do that. What I mean by general skills, first, these are text data. So understand, I mean, languages is probably like something I want to learn, even though we don't teach anything about language. So there are maybe like 100 languages that we fit into the model. And so learning all those, probably very useful to at least understand the syntactic structure of it. Second, after that, I want to understand the language so that I can kind of, that's applicable to pretty much most of the sentences, next token prediction. And third, maybe more like reasoning to compose the concepts. I'm just making things up, but I think these are like, if I'm doing this task, I will probably think about those. And at some point, that's the pressure given to the model. So so I think that that's crucially, we don't directly teach any of these general skills. And they are just incentivized by this learning objective and the data, and these abilities emerge. And abilities that emerge are typically more general, probably because it's driven from the need to develop general skills. And so you might wonder, okay, this weakly incentivizing the model requires a lot more compute, and hence it's an inefficient process. And I would like to think about it this way. It enables adding more compute. And we'll have more compute. So this is a more scalable training strategy. And that, I think, is why this has done so well. And maybe let's generalize this hypothesis a little bit. For a given data set and learning objective, there is an explicit learning signal and a set of induced incentives. So for this next token prediction, the explicit signal was to predict the next token, because that's the task given. The induced incentive is to learn general skills so that it can do many tasks as possible, like understand language, reasoning, and so on. What are some other examples? Playing chess with 0-1 reward at the end of the game. If you think about something like AlphaGo 0, the explicit signal is to win the game. And we don't teach anything other than that. And so the induced incentive in this case is learn what good moves are. And the model might not even think about what is good, the notion of being good, but it's just, that's the incentive. It has to know kind of those in order to win the game. And if we, for chess, the environment is so narrow that it probably doesn't matter. But if we use this kind of process, what it learns, winning the game maybe matters, but the general notion of what is good in this environment is something that is very general. And I think we should increasingly care more about that. Third example is probably more relevant for nowadays. Hallucination, I think, is one of the core problems that is unsolved for the language models. And so here's one example I got from Sean's talk here, and adapted for my purpose here. Reward structure for, let's say we are doing simple question answering, and the model hallucinates on this answering simple question. We can define something like this. One reward is 1 if the answer is correct and unhedged. And 0.5 if correct, but the model says, I'm not really sure, but maybe this, and got correct. 0 if the model says, I don't know, which is an important class of answers. And third, and -2 if the answer is hedged but wrong, and -4 if the model is very confidently wrong. And this structure, what is the explicit signal is that the answer, we answer the question correctly. That's the explicit signal. But what is induced if we do this with trillions of questions, let's say, is that the model needs to know what it doesn't know. Let me explain what that means. So here, if I give you like 100 questions and you don't know the answer to 50, you can kind of memorize, okay, this question I don't know the answer, and so on. But if I give you like trillions of them, then it's easier to think about, instead of tracking each of those trillions, which one I know and which one I don't know, maybe think about the general notion of what it means to know something, what it means to not know something. And that ability is kind of what might emerge out of this kind of induced incentive structure. And that, I think, is the only fundamental way to solve hallucination. And maybe just to give you a loose analogy of this process, we have this old saying that says, give a man a fish and you feed him for a day. Teach a man to fish and you feed him for a lifetime. So you can think about the first one as like a hard coding, second one directly teaching a skill. What is the incentive-based kind of approach for this problem? It's teach him the taste of fish and make him hungry. And then this person, if it's enabled, will go out, learn many, many skills, including fishing. And along the way, the induced incentive is that he'll learn some other things, like patience, being patient, learning the weather, knowing what bait this fish likes, and so on. And these might be more general skills, like being patient is quite general. So that's kind of my loose analogy extending this old saying. And so looking at this, you might wonder, okay, this is very inefficient. Why would you even do that? And there exists a trade-off of achieving the goal versus taking so much time. And more generally, what we're thinking about is trade-off exists in this kind of situation. When there's a trade-off, there's a scarce resource that we're thinking about, and that is, in this case, a time required to get this job done. So if we plot it on the x-axis for the time required to get it in each method, it takes a lot more time to incentivize him to learn the teaching skill, the fishing skill itself. But that limitation is for humans. For machines, the scarce resource we're talking about when thinking about the trade-off is not time. It's time, but increasingly it's more about the compute required. And we can get away with this. And this has a quite rich implications. And one of that is I hear a lot about, okay, we have a small specialist model that's probably better than some generalist large model. And when I hear this, the hidden assumption here is that small specialist models can win in a narrow domain because there is some kind of a trade-off between being a specialist and generalist. I think this is the bias we get from just being a human. Why? Because, again, trade-off, we want to think about the scarce resource, which is time. And most humans operate with pretty much the same time budget. And like you may sleep like 1 hour less or more, but roughly like 16, 17 hours a day, that's kind of what is given to humans. And because of that, time spent not being a generalist is time spent on, or time spent being a generalist is not spent on being a specialist and vice versa. So that's the trade-off. But for machines, it's not that at all. One model gets to enjoy a lot more compute than others. So if you like this Dragon Ball, there's a room of spirit and time where you train 1 year inside, it's a day outside. So in this case, a person who has access to that kind of thing has 365 times more time than others. But when we talk about machines, the multiplier is not just 365, it's a lot higher. And I think that's the situation. So I don't think this trade-off exists at all. If anything, generalists are actually better at special things. And this incentive structure, you might be wondering, this is a very old idea. If anything, entire human civilization probably is driven by incentive. And even evolution might be thought of as an incentive structure for survival. So why am I talking about this old idea? Why is it now relevant? That's the thing I need to mention. And let me start with this. No amount of bananas can incentivize monkeys to do mathematical reasoning. So even if the reward is infinite and incentive structure is perfect, just not going to work. It's not possible. And what that means is some kind of a threshold intelligence is necessary for the given problem to work with the incentive structure. And currently, with something like GPT-4, we crossed that threshold for many, many tasks. So I think it certainly now suddenly makes sense to think about incentive-based structures to teach the models what we care about. And that brings it to this notion of the incentive structure depends on the model size or model scale. What abilities emerge depend on the model size. That's one interesting parameter. And if the model is too small, model might give up on developing these general skills and just leave it the simple heuristics and just fine with the high loss during the training process. So that sums up the incentive structure part of it. And I've been talking about this immersion abilities a little bit in a loose sense. I want to talk about that. So in particular, we are talking about some abilities emerging when we scale up. And this requires really having the right perspective. And in the field, we have some discussions around, okay, the emergent ability is a mirage or emergent abilities don't happen and things like that. I don't think the details matter. Let me give you one way to think about it. I make the tiniest transformer, the D model is two layers, tiniest transformer model, and take some task that works with GPT-4 and say math, and then you solve it with this. It's not going to work. And it works here. So there's some kind of inflection point there. And for any problem, you can find the smallest possible model that doesn't work. And if it works with the current model, to me, that's emergence. So I think that's very easy to prove that it actually happens. And if it doesn't, then problem is not interesting enough for me. And this is what I mean. X-axis, some scale, and then it doesn't work, and then at some point it just emerges. Doesn't work for everything, but for many interesting things like reasoning, this is the pattern we see over and over. And the first perspective that really we need to think about is this perspective of yet, because now things that don't work now doesn't mean that it will not work later. So what we should do is instead of saying this idea doesn't work, we should say this idea doesn't work yet. And that really is unnatural for humans to think about. And I think there's because the bias is so huge in how we operate in this environment. We are operating in an environment with underlying axioms not changing often, which is kind of the physics. So if you run like, I don't know, thermodynamics experiments now, and you get the result, you run that 3 years now, and it will probably be the same. For that matter, 300 years, probably the same. And we're used to this kind of environment. So because the underlying axioms are the physics we are operating. And for language models, what is that equivalent concept of the axioms that we're operating under? And that is more like the most capable model. So when in 2020, GPT-3 came out, that serves as an axiom for researchers to build intuitions on how to leverage this kind of technology. GPT-4 came out last year. It changed a lot of the things. And many things that build on top of that old model are not relevant. It's almost like every couple of years, we move to a different planet and the physical understanding changes. And this calls for the need for kind of a constant unlearning process. And the intuitions and ideas built on top of those incorrect axioms now have to be unlearned, but I don't think this is done that often. So, which acts as an interesting dynamics for newcomers. And in the field, I see a lot of times that undergrads with not much research experience come in 1 year, they write papers that change the trajectory of the entire field. And that is not possible if you think about in theoretical math, physics. I don't think that that's possible unless you go back to like Gauss or something. So this is a really interesting dynamics. If you come in with not much knowledge, you might think of yourself as having not much baggage to unlearn, and you're more flexible. At least that's how I thought about it. And many people at OpenAI are not traditional ML PhDs, and they're more like just when they see the evidence change, and we always adapt to new paradigm. And so that's, I think, it's really important dynamics I want to point out. So how I think about it, again, one last cartoon, and then we can wrap it up, is this emergent ability, if we think about some scale on the x-axis, and then abilities for the y-axis. And I put two models of different sizes, 3 and 4, doesn't matter. Let's look at the ability 1 first. And ability 1, we have GPT-3 and 4 are before this inflection point, so it's not possible. But just a little bit better model than GPT-4 might be able to get some sign of life. Ability 2, it will take a lot longer. Ability 3, even GPT-3 is able to do it. For example, this might be like sentiment analysis, things like that. So what I mean by this, whenever we see this ability, because we don't have any theory for emergent abilities, there's no way to know which ability I'm working on. But at least having this kind of visual picture can I can use this to prepare myself. So I don't want to work on, as a practical person, like ability 2. I want to work on ability 1 and just be prepared for the next model and think about why this is not working. Where can I put more compute to get to the sign of life? And maybe less so. There's nothing wrong with this incremental thing, but if I'm working on things that small models can already do, I need to know that there's finite room of improvement. Let me close this talk with just summarizing what we have talked about. The most important underlying driving force is the compute cost is decreasing exponentially. And AI researchers' job, recognizing this, is to not compete with that and just leverage it by designing more scalable methods. Current generations of language models rely on next token prediction, which can be thought of as a weak incentive structure, which needs to learn general skill so that it can handle trillions of task types. And more generally, we should start thinking about next token prediction has been great, but it's not the only thing. And we should really think about incentive structures for the models. And that's the new kind of learning paradigm we should really engage in. And emergent abilities happen, which is one of the unique things about the language model. So we need to have some right perspective, and such as unlearning things that are based on outdated axioms. That's it. Thanks.